Good morning, everybody. Buenos días todas. Can everybody hear me okay in the back if I talk this loud? Okay, great. Well, let me start today by giving an overview of where I'm going to be headed in the next 17 minutes with my presentation. First, I'm going to survey recent attempts by scientists to create a specific type of emotion that is empathy in robots and in artificial intelligence. And then second, I'll discuss other incremental steps related to the more long-term project of creating broader emotions in artificial intelligence. And last, I'll finish with some reflections on the implications of this for the Metabody project. Service robots, which include things such as automated milking machines and military drones, as well as domestic and personal robots, already vastly outnumber industrial or factory robots. This chart of the world robot population you see on the screen by the Institute of Electrical and Electronics Engineers, IEEE, shows just how many more service robots we have than industrial ones and how rapidly they're increasing. Another way of looking at this is via the statistics of the International Federation of Robotics, the IFR, which is the major trade group for robot manufacturers. Their data show 2.5 million personal and domestic robots sold in 2011 alone, and that is more than all of the industrial robots ever sold from the 1960s to 2011, which amounts to about 2.3 million. These domestic and personal robots need to be attractive to consumers and safe for them to use. So, affective robotics is gaining steam rapidly due to these needs for friendly and safe AI. Now, this last little bit on the slide is only partially a joke. As many of you probably know, in 2010, Dick Cheney was given an artificial heart, a centrifugal pump, that has no heartbeat because it swishes. So for 15 months he had no heartbeat, which may not be news, but he was also a cyborg. Another reason that empathy is trying to be developed and these affective robotics is being looked into is because another bigger sector of what are called service robots is military, and obviously safe AI is an important consideration there as well. Empathy is what most scientists see as the basis for friendly AI and good social interaction between robots and humans. So a lot of the research being done to improve human-robot interaction, or HRI, is mainly in the area of generating empathy in robots and creating it toward robots in humans. Let me illustrate what I mean with a few recent examples. The first example, a group of researchers funded by the same kind of grant Metabody received. This group's funding came from the European Union's Platform 7 agency. They used empathic robots as teaching tools for elementary school students. As they said, and I'm quoting here, the goal of LIREC is not to build robot companions that replace human contact, but rather to design companions that fulfill their tasks and interact with people in a socially and emotionally acceptable manner, end quote. In one of their experiments reported in a recent article that you see on the screen here, they used an empathic robot called iCat to teach students how to play chess. Now, you see this robot, which is made in Germany, has an expressive mobile face, so it can have facial expressions. It also has sensors on its ears, those little things on the ears, so if it's touched, it can sense the touch and react empathically to the touch. It also has sensors on the feet for the same thing, and a speaker, and in its nose is a video camera, so it can see what expression you have, and basically it's meant to mirror the expression or give an appropriate expression based on what the student does. Now, when they were teaching them to play chess, when a student had trouble, the robot would use one of 4 empathic responses that were programmed into the robot. The first response was encouraging comments. The second response available was offering help. The third was to make a bad move intentionally to encourage the student not to quit. And the fourth was what the experimenters called scaffolding. And they defined that as providing feedback on the user's last move, and if the move wasn't good, to allow the user to play again. POM, as they called it. Now, that means they gave it an algorithm that allowed it to infer from other robots' actions what that second robot might do next, and how the robot reasons. Essentially, theory of mind is the ability to understand another person's intentions, or in this case, another robot's intentions. Humans commonly use theory of mind to make inferences about others' feelings and states of mind. Kim and Lipson's main goal, and I'm quoting here again, was to develop controller inference algorithms in robots that could help in interaction with non-robotic actors, such as humans. The experiment was considered by them to be successful because of the algorithms that could evolve with experience. One robot was able to infer what another robot was going to do. Now, this was a tightly controlled experiment. The first robot on the screen, and the robot's represented by, it was a little ball with wheels on it and a CPU, a central processing unit inside the robot. That robot's job was to try to navigate to a light on the other end of the room, and it would take different paths because it had to figure out its way to this light. The observer robot would watch that first robot try to navigate and then infer, as it watched that robot, what the robot was going to do next. And at first it didn't do very well, but the evolutionary algorithm programmed into it allowed it to learn and evolve, and it got better and better at predicting the first robot's actions. And then they introduced a third robot that was sort of a first recursion, as they called it. This third robot would watch the second robot watch the first robot and try to predict if the second robot could predict the first robot's actions, and that worked as well. Now, the long-range implications of this are pretty obvious to me, that to enable robots and other artificial intelligence to read the internal state and intention of humans, which was the purpose of the experiment in the long run, and thus to bring them one step closer to an emotional interface with humans. So then, do robots feel empathy? Does this mean they feel empathy? Have experimenters succeeded yet with that? The answer so far is no, not really. As of now, they just simulate physical markers of empathy. And you can see the 6 basic emotional faces here on the iCat that the iCat is programmed to display. And you can see, for instance, in the upper left-hand corner, a neutral expression, the upper right-hand corner, a happy expression. Now, despite the fact that they are unable to actually empathize with humans, there's a slight problem. Humans actually develop real attachments toward and empathy toward robots. Human empathy toward and attachment to robots is discussed by Matthias Scheutz in his chapter in Robot Ethics, and he gives a lot of examples in this, gleaned from various studies. One is somewhat surprising to me, and it's the fact that many people form emotional attachments with their robotic vacuum cleaners. These are called Roombas. I don't know if anybody here has one. I have 2. I don't have an emotional attachment to them, but they certainly clean pretty well. These simple devices, if you don't have one, they're simple devices that merely clean your floors. You program them for the time you want them to run, and they basically run in a grid-like pattern, bumping into things until they've covered the whole room. Then they dock themselves to recharge. Many people, not me, personify them, and some even form such a sense of gratitude toward these robots that they actually clean the floor themselves in order to give the Roomba a day off. This has been found in studies. Many also dress them up in these costumes that you can buy, and thereby make them into sort of fuzzy little interesting things. Now, especially concerning to Scheutz is the possibility is the possibly dangerous behavior that such attachment causes. Scheutz chiefly worries that such a one-way attachment will make humans emotionally vulnerable to manipulation by robots via their human or corporate sponsors or makers. For instance, he foresees that if humans buy robots they get attached to, and the robots are socially active, can talk to them and so forth, carry on conversations, then the robot could be programmed to sell more things to those people, to suggest, hey, you know, why don't you buy the next robot, or why don't you buy this other product from our company? And that's just a mild example of the vulnerability that a human could have. He also talks about soldiers' attachment to their bomb disposal robots in recent conflicts in Afghanistan and Iraq. In these cases, it's not just a matter of wanting to clean for the Roomba or to dress it up because you're emotionally attached to it. Personifying bomb disposal robots makes soldiers reluctant to trade them in for new ones once they have become too damaged to function properly. This is also a finding of a study. And obviously, this could cost soldiers their lives. So, what about this uneven reciprocation of emotions between robots and humans? Robots can't feel emotion now, but could they ever? The answer is maybe, but much stronger artificial intelligence is needed before we get emotions complex and advanced enough for projects like Otto Rossler's benevolent artificial intelligence or Ronald Arkin's artificial conscience in military robots, both of which I've discussed elsewhere. And there are books and articles written by these two people talking about this. A number of distinguished scientists at last month's Global Future 2045 conference in New York City, which I attended, agreed that what we're working with now isn't sufficient. Stuart Hameroff and the great physicist Sir Roger Penrose, who've been working together on the theory that human consciousness operates according to quantum physics, and the eminent computer scientist Marvin Minsky, the distinguished genetic engineer George Church, the computational neuroscientist Randall Cohn, and other noted scientists from across the disciplines who were all at the conference, argued that we have to move beyond standard computing and scientific thinking, and that the key is computing at the quantum or molecular levels and other neurophysiological advances at the microscopic level in order to advance either human enhancement or artificial intelligence. Moreover, although the big problem for these more advanced types of projects like Rossler's and Arkin's is insufficient engineering, there's also a large philosophical problem, and that is our perennial disagreement as to what basis we would use to define proper ethics. When thinking about values like benevolence or conscience, especially given different cultural viewpoints, Kantian deontology, based on pure duty and rule-based ethics, Buddhism, based on essentially selfless compassion, and utilitarianism, the greater good of the many, are just a few of the philosophical systems that have been proposed as a basis for artificial intelligence ethics. And I plan on investigating everything I've shown you further in the coming period of the Metabody project, including especially the philosophical dimensions of it. There have been some engineering inroads made toward the longer-term goal of creating complex emotions in AI. Now, although we may have a long way to go to create molecular or quantum level computing that leads to super powerful AI, some elements that are part of emotional response in AI are possible now because of recent incremental successes with cognitive features that contribute to emotions. For example, not only have Kim and Lipson succeeded with their theory of mind experiments, but by using evolutionary algorithms and computing, they've also done much more, such as their more recent experiments, this is 2010, creating replicas of neuronal activity at the molecular level. And what you see here is a model this is from their study. What they did first is they took microelectrodes and implanted them in a neuron from the brain and measured the voltage going across the intracellular space. Then they fed all of the data into an evolutionary algorithm, and the algorithm turned out an artificial version that functioned exactly the same way, including with the proper capacitance and resistance. it wasn't quite good enough, but then it was tested virtually, and then with the mistakes clarified, the algorithm improved and improved until it got this final circuit that functioned exactly the same way as a biological neuron. Most remarkably, I think, is this experiment by Theodore Berger and his successes, and these are very recent successes, with long-term memory regeneration and generation. This is by using implanted chips to replace damaged parts of the hippocampus in rats and monkeys. Now, what he did is he did the same thing. He basically did a data dump from, he created algorithms and programs, this is at USC, that could receive a data dump from the hippocampus of the rat, for instance, and then using algorithms recreate the data, the memories. He found a way to create virtual memories. And then when that part of the hippocampus was removed and replaced with a chip, the rat was tested, had lost its memory for how to navigate a maze. When the chip was implanted, the rat had the memory again. The long-term memory reappeared from the chip, and the rat was able to navigate the maze. Now, if memories can be artificially generated, and he said he could artificially generate memories that did not exist in rats as well, and if that's true, then it brings the possibility up of generating emotion via chips as well by using them to replace parts of other brain structures, such as the amygdala, which is the seat of empathy. So let me conclude with some preliminary reflections on the implications for all of this for the Metabody project. First, if the point of the project is to investigate whether there is, as stated in the project proposal, quote, an increasing reductionism of movement in the nonverbal spectrum to patterns of imitation and functionality, the answer appears to be yes, that's exactly what's happening here in the scientific world. But from the point of view of roboticists, to be fair, this is just for the short-term goal of studying the visible part of human emotional reaction. The eventual goal is something more, to replicate true emotion, and the roboticists would probably not see this as reductive. Do we see it as reductive? That's another issue for us to study in the coming years. In answer to the second part of the project's investigative query, does the increasing juxtaposition of the human with the digital undermine human kinesthetic communication processes? Maybe. Right now, yes. But in the future, the answer to this depends on what sort of perspective one takes on the long-term goals of artificial intelligence researchers. From their perspective, they're trying to replicate those same kinesthetic communication processes and in all of their spontaneity, because their ultimate goal is to create robots and AI that are humanoid and, importantly, are emergent, that can, in other words, evolve. If that occurs, then perhaps new hybrid AI-human kinesthetic processes will evolve as well and be spontaneous processes in a very high-functioning AI. But that's a really big if, and from what most scientists say, a long way off. Thank you very much.